So next up we have Daniel Fone, hailing from Christchurch. Woohoo!
Thank you. If you are like me, you have probably struggled with date time programming. In fact, I'm pretty sure I have code in production right now that handles dates and times incorrectly, which is okay because Lena says we can make mistakes. Even so, perhaps you've imagined abolishing daylight saving, perhaps you have imagined radically reforming the calendar. Let me suggest, though, that inventing a new date timekeeping scheme is not the solution it promises to be. Instead, I want to help us to embrace this challenge. And I want to do this in two ways this morning, this afternoon even. I first off want to explore the history, the very human history of date and timekeeping and the reasons behind our conventions. And then I want to see how this plays out in the code we write. And I want to do it a little differently. Rather than start with some little hook like the fact that Unix time goes backwards, no cheap tricks like that, I want to give you my conclusion up front. And maybe this won't make sense straight away, but I hope that if you bear it in mind as we take a look at the history and as we explore the code, that you'll see that this is a helpful way to approach the problem. Because generally I see two approaches to this challenge. The first one is that there's just one thing you need to remember. Always use UTC in the database, or always use Unix time when you're in your code, and maybe there's some validity, but typically I think this is an oversimplification. On the other extreme, timekeeping is a disaster, it's a nightmare, we should just abandon all hope of ever getting it right. My conclusion is hopefully a middle ground. Timekeeping is a social construct. It's determined by geopolitics. It's not mechanical, so I don't think there's just one thing you need to remember. But there is a helpful way to think about and to frame this problem. And that is that timekeeping is not about time. It's about clocks and calendars, and specifically whose clock and whose calendar. Because we're never dealing with a point in time. We're always dealing with a point on a clock. And that clock belongs to someone, and we have to know who. Maybe this doesn't make sense just yet, that's okay. To unpack this, I want to explore about 50,000 years of human timekeeping history in about 10 minutes. So get comfortable, buckle in, we're going to go very fast. You can just watch the video on half speed if you need to catch up later. 50,000 years ago, the dawn of behaviorally modern humanity, we are in small hunter-gatherer tribes. The first thing we notice without a roof over our head is this, going up and down and up and down. And then this as well, going up and down, but also changing shape and periodically disappearing. And these going up and down, but also tracking across the sky over a long period of time. This is the Lobombo bone. It is a 40,000-year-old monkey leg. It's got 29 notches, and anthropologists believe it could have been tracking the lunar cycle. This is maybe one of the very first date.news, someone's calendar. Similarly, this is Warren Field in Scotland. It is a 10,000-year-old calendar aligned with the 12 lunar cycles of the year. It's the oldest archaeological evidence we have for the observance of the year. That is about twice as old as Stonehenge, which is another calendar aligned with the yearly equinoxes. So, boom, we've got a day, a month, and a year. And this serves us very well for a long time. But 5,000 years ago, beer and bread brings us together into cities, and cities need projects. And as we know, projects need 9 a.m. stand-ups. And you can't get to stand up unless you know when it's 9 a.m. So you stick a stick in the ground, boom, you've got yourself an hour. 2,000 years ago, we're making good progress. All the major players are on the calendar. You can ask me later about a week because that's just too complex and fascinating to cover now. The problem, though, is that our days and our months and our years, they don't sync up. The sun and the moon and the earth, they don't spin in time. The Romans, for example, they had 12 lunar months in a year. 12 new moons, and that's a little bit shorter than the actual year. So every so often they would just decree a full extra month, a full extra moon to catch up with the tropical year. The problem with this is that the officials who decreed the leap month had fixed length terms in office, and they raised taxes and troops based on this, so you can imagine the shenanigans. Julius Caesar comes along, he says, no more shenanigans. The year is about 365.25 days long, so we're going to forget about the moon. We're going to have a fixed length year, and then every 4 years we will have one extra day. Boom, predictable, scheduled Julian leap days. No more gerrymandering the calendar. This works pretty well, again, for a long time, but as they knew at the time, the year is a little bit shorter than 365.25 days. So by the 16th century, the seasons and the equinoxes had drifted 10 days off. So for a variety of reasons, politics and power and a little bit of religion, Pope Gregory XIII decreed a new calendar. Not so many leap years, and to catch up with where the seasons should have been, they skipped 10 days, which meant the 4th of October, 1582 was followed by the 15th of October, 1582. Boom, calendar reformed, if you're a Catholic state. The Protestant countries, they don't care so much about the papal bull. They're going to do things on their own time. The British Empire waited about 200 years until they eventually skipped 12 days to catch up with the Gregorians. The Swedish Empire, they figured that skipping all those days at once was just too hard, so they figured they were going to skip leap days for 40 years. Great plan. They were going to catch up eventually, and they started doing this, but then they got embroiled with this war, and they forgot to update their calendar, and they got out of sync with literally everyone, including themselves. So for the first and only time in history, they had a February the 30th to get back in sync. The Russian Empire was so late to the Gregorian party that their shooting team in 1908 turned up 11 days late to the London Olympics. We have made it to the Industrial Revolution, and at this point, apart from those few late hiccups, the calendar is a pretty settled thing. Clocks are also fairly straightforward in the pre-industrial world. The sun is really the ultimate authority, and every city, every port keeps its own time based more or less on the position of the sun, which blows my mind. Every city had its own time. Now, this works all right when travel and when communication is slow, but trains and telegraphs completely screw this up. You imagine trying to schedule a train timetable where every station on your track keeps time 10 minutes differently. Absolute carnage. In New Zealand, it was the telegraph office that drove things. One operator complained that in Hokitika, the telegraph office closes whenever it pleases because there is no public time in Hokitika. So November the 2nd, 1868, the little British colony of New Zealand was the first country in the world to adopt a national standard time. We had the very first time zone. And that was, yeah, why not? I think we can call that an accomplishment. That was GMT plus 11.5 hours because that's roughly where we are in the world longitudinally. The next major innovation in timekeeping was the still notorious daylight saving. And the original idea behind this is that because we don't go to bed when the sun does, if we can push a little extra light and warmth into the evening, we can save energy. Whether that's true or not is debatable, but it was particularly important during the war. So 1941, we had an emergency regulation decreeing daylight saving, pushed us 30 minutes forward to GMT plus 12, and of course we ended up staying there. As time went on, the labor unions got on board to give workers more sunlight after their workday, and currently we observe, I believe, more daylight saving time than standard time in New Zealand. So I don't know if it's really standard time anymore, but nevertheless. Similar situations play out all around the world. Boom, we have our modern time zone system. Now, you might think that time zones look like this, but this is a little bit misleading. Because while this might be true today, it might be true tomorrow, in reality, every jurisdiction makes its own rules. The definition of a time zone is any region where the local clocks all agree. The time zones are just any region where local clocks all agree. A time zone is about a clock, and those clocks can do very strange things. Samoa, for example, was originally aligned with Asia, 4 hours ahead of Japan. About 100 years ago, American traders convinced them to repeat July the 4th, no coincidence, repeat July the 4th and align themselves 3 hours behind California. Perhaps this is okay at the time, but fast forward 100 years, in fact, to 2011, and all of their trade and their expatriate community is on this side of the Pacific. So, in 2011, Samoa skipped December the 30th just to realign their weekdays with Australia and New Zealand. Now, Samoa and American Samoa, about 200 kilometers apart, they keep completely different days. They're 24 hours more, in fact, 24 hours different. We cannot think about time. We have to think about clocks and calendars and whose clock we're talking about. Egypt and Libya, in very recent history, both cancelled daylight savings with almost no notice. Turkey extended daylight savings so that they would have more sunlight at the polling booth during election, but they didn't let anyone know, so everyone's smartphones were still wrong, and it was chaos. Ultimately, clocks obey the rules of government and not their little internal mechanism in the back. Now, a lot of people get to this point, they think, okay, a timestamp is not enough. We get that now. Maybe if we can just have a location as well. We have a time and a location, and we can geolocate the time zone, and we can work out the offset and the daylight saving rules. That is still not enough. If you live in the West Bank, the time zone you observe depends on your ethnicity. So Israeli settlers, they follow Israel time, and the Palestinians follow Eastern European time, which are almost always the same, except daylight saving kicks in on different days. Such that one time there was a car bomber who failed to take into account the different time zone, and their car bomb detonated harmlessly to everyone except for the car bomber in a completely different time zone. I have no adjectives to describe that. One final quirk before we can wrap up our history of timekeeping. It used to be that a second was defined as 1/60th of a 60th of a 24th of a day, of a mean solar day. These days, a second is defined related to the activity of a cesium atom. Because, as many of you perhaps know, the Earth in its old age is slowing down, which means that every year the average day gets a little bit longer. And to accommodate this and to keep this in sync with our clocks and calendars and what we see in the sky, the International Earth Rotation and Reference Systems Service inserts leap seconds into UTC just whenever it needs to, not unlike the months in the Roman calendar were decreed whenever they needed to be. Fortunately, I am not aware of any political manipulation of this yet. I'm sure it'll come. Okay. Let's slow down a little and let's talk about some code. I am not going to go through the classes in great detail because there is just too much to unpack. But what I want to do is give you enough context and enough of a framework so that you can read the documentation for yourselves and it'll make sense, which granted is not always easy. It can be confusing just to know how to represent dates and times in Ruby if you start looking at the documentation. We have got the date class, we have got the time class, and we have got the date time class, and these exist in core and standard library and active support. You have a lot of options. Fortunately, I think it's easier than it looks, or well, simpler at least. There are really just two ways to model clocks and calendars in Ruby. On the one hand is the time class, and that models Unix time, and we'll come back to that in a minute. The other way is this pair of date and date time classes, and they model the calendar. In particular, the date class represents two things: a number of days since a historical day 0, which is not entirely random, but it doesn't matter what day it is. And secondly, the day number of calendar reform, which is just when the rules switched from Julian to Gregorian. And as we know, that happened on different dates for different countries in history. The date time class allows for fractional days, it allows for a GMT offset, but really it only models pre-industrial timekeeping. And even the Ruby docs will say you pretty much definitely want to use the time class unless you really know what you're doing. So if you're wondering, don't use datetime, just use time. In this example today is day number 2458061, and the reform day is day 2299161, which is the default, which is the day of Italian, the original calendar reform. And armed with these two numbers, and armed with all the rules for Julian leap years and Gregorian leap years, the date class can give us this very accurate model of the Western calendar system. It will tell us what the previous day was, and what the next day is, and what the day of the week is, and whether it's a leap year, and all of these things, which, as we know, is not always straightforward. Here's an example from the original reform of the calendar. There is no 5th of October. The day after the 4th is the 15th. Now, you might be wondering at this point, when will I ever care about calendar reform? And my hope is that you never do, and probably you won't. But just in case, here's a little example from the Ruby documentation. Two great writers, Shakespeare and Cervantes, died on the same date, the 23rd of April, 1616. But they did not die on the same day. Shakespeare died in England before it reformed the calendar, so it was still observing Julian rules. And you can see there that the day number of Shakespeare's death is before the day number of the English calendar reform, which is represented by that date England constant. Cervantes, on the other hand, died in Italy. After it had reformed the calendar, it was observing Gregorian rules. So these two dates represent different days, and you can see that Shakespeare actually died 10 days after Cervantes. Nevertheless, UNESCO declared the 23rd of April World Authors' Day. So I guess we'll just celebrate it anyway. Hopefully you'll never have to worry about that again. The time class, on the other hand, is extremely common and popular and probably useful in modern software development. But it can be quite confusing, and I think that's because all it's doing is providing a relatively thin object wrapper around some libc timekeeping functions. And like many other Ruby core classes, if you're not familiar with the underlying libc implementation, it can be a little bit hard to understand how and why these classes work the way they do. So rather than take a look at the time class, we're going to take a look very briefly at how libc handles timekeeping. And hopefully, with that knowledge, you will be able to come to the time class and read the documentation, and it will make a little more sense. There are two ways to represent time in libc. The first, and probably the most familiar, is Unix time. So this is, and many of you will know this, this is the number of seconds since midnight, January the 1st, 1970 UTC. Minus, and this is the part not so many people know, minus the number of leap seconds that have elapsed since then. So every time there is a leap second, Unix time goes backwards and repeats that second. It is an ambiguous time format, which is actually really hard to deal with. But apart from that one edge case, the idea behind Unix time is that it's easy to calculate durations and distances because it's just a number. It's just a single number. The other way to represent time in libc is with this broken down local calendar time. And you can see there's a bunch of fields, a bunch of attributes on that struct that represent components in our calendar. And it's mostly integers. Just watch the indexes. The day of the month is indexed from 1 to 31, which is what you'd expect. The month itself is indexed from 0 to 11. The time class fixes this, but then does it the other way around on one of the other attributes that it offers. So watch out for that. So libc allows you to do calculations and encourages you to do the calculations with Unix time and then convert to the user's time into this local time struct. And it does so using the Gregorian rules the whole way. That's called the proleptic Gregorian calendar. If you ever encounter that term, it just means it uses the Gregorian calendar the whole time, and it'll be wrong historically, but you almost certainly do not care. The question is, how does it determine local time? And this is relatively straightforward once you dig in a little bit. The first thing libc does, and time class is just wrapping the same behavior, the first thing it does is it looks for this tz variable. If that's not set, it will look in a few different places, most notably etc local time, which on my Mac and most other Unix-like systems is a symlink to user share zone info Pacific Auckland. If you're on Windows, it's a different system. I'll leave you to figure that one out by yourself. But here, both of these are pointers to the IANA time zone database. And this is the canonical database for all the time zone info, for all the world, for all of recent history. To give you an idea of what this looks like, here are the rules for New Zealand. You can see at the top, this is highly abridged, by the way. You can see the first 4 rules there are our daylight saving changes through history, the years they were applicable, the date and the time they come in, and the offset change. The rules down the bottom, you've got our zone name, you've got the original GMT offset 1139.04, which is based on the meridian of Auckland Harbour itself, the local mean time. You've got the 1868 transition to GMT plus 11.5, and then the post-war transition, permanent GMT plus 12. So libc, and hence the time class, lets you represent and do calculations with 2 clocks. UTC via Unix time, and the system time zone. Now, we can fiddle around with the TZ variable, but you can imagine that gets very hard to manage at an application level. So if we're dealing with multiple time zones, this is not enough. If we want to have users with different time zones, with different local clocks, we need to reach for a gem like TZ info, if you're a Rubyist. If you're not a Rubyist, I can't help you here. TZ info is basically just a wrapper around the IANA time zone database that it expects to find on your file system. It can be a little unwieldy though, so most Rubyists are probably familiar with active support from Rails, of course. And active support is just taking a Unix timestamp, it's taking a TZ info object, it's wrapping that into a TimeWithZone object, and then it's monkey patching all the classes so that they do the right thing with times and with dates, and you can advance them and set the time zone, etc. The documentation is actually pretty good once you understand the principles behind it. So if you want to see the mechanics and how to wield this in practice, go take a look at the Ruby guide or the Ruby class documentation. That is the time class. That is the date class. That is about 50,000 years of history. If you like the big picture, if you like the context, hopefully that's helpful. If you just want me to tell you what to do, I don't think there is just one thing. I think it depends what you're trying to do. I think it's more nuanced and complex than that. But I will say this. Be explicit about whose clock you're dealing with. Whether you're storing times in the database or manipulating times in your code, always be dealing with an explicit clock. Because if I give you a timestamp and ask you what will the time be in 1 second, you cannot tell me the second because of possible leap second changes. You cannot tell me the hour or the minute or the offset because of daylight saving transitions. You cannot even tell me the day, and it occurs to me now, the month or the year because of arbitrary time zone shifts. You cannot tell me any of those things with certainty unless you know whose clock this represents. And to identify these clocks, offsets are not enough. UTC plus 3 could refer to Moscow all year round, but only largely since Putin's been in office. It could refer to most of Eastern Europe, but only during the summer. It could refer to Sudan, but only up until a couple of days ago when they shifted to UTC plus 2. It could or could not refer to South Sudan because no one on the time zone mailing list has been able to get hold of anyone in the government of South Sudan to know if they're going to follow Sudan or not. Abbreviations are not enough. CST could refer to anything from UTC minus 6 to UTC plus 9.5, depending on who you ask. There is no canonical list of abbreviations. They are ambiguous and they change. The best systematic representation of the world's clocks is the IANA time zone database. Here's where I want to land this. Timekeeping is nonlinear. With leap seconds, with historical calendar reform, one day doesn't necessarily follow the next. 1 second doesn't necessarily follow the next. Timekeeping is unpredictable. With arbitrary time zone shifts, with daylight saving law changes, with leap seconds, you cannot precisely predict the times of future clocks. Timekeeping is anthropocentric, which is just to say that people decide what the clocks say, and not geography and not astronomy. Especially if you're the resident of a contested region like the West Bank. Because ultimately, timekeeping is a social construct, just like language and finance and gender and all of the other things we invent to keep humaning. It is a social construct. Now, granted, it has some basis in an observable empirical reality, and that might tempt us to think that there is some more true or more real or more pure version of time. But UTC is just a clock. Unix time is just a clock that goes backwards. GMT, UT0, UT1, TAI, these are all just clocks with their own definitions and with their own purposes. If our users are human, we need to use clocks and calendars and not time. It is going to be messy, it's going to be complicated, it is going to be inconsistent because that's the way we are, so we might as well learn to love it. Thanks everyone, it has been a pleasure. I have done way too much background reading on this. So if you've got any questions at all, ping me on Twitter, ping me on the Ruby New Zealand Slack, come and talk to me afterwards. I'll probably hang out in here for a little bit. Otherwise, just find me somewhere. I'd love to chat. And if you think timekeeping is hard now, just wait till we have a colony on Mars. Thank you very much.